All right, guys, I'd like to give you a quick overview of how we're going to go about doing the calculations and stuff for this lab. Again, to remind you, the purpose of this lab is we're trying to figure out the rate and order for this reaction right here. In order to do that, you collected a bunch of data. So let's look at specifically what data should you have collected. First of all, you should have some graphs attached in your notebook. Every person should have their own set of graphs. For each graph, you should have a title on there. If you didn't print a title off, then I would write one in by hand just so it's clear what that graph is showing. I know that most of you have parts 1 and 2 on one graph and parts 3 and 4 on another graph. Make sure that those are clearly labeled. The default that the computer gives you just says something like run 1 and run 2 or latest. We want to actually see like part 1, 2, 3, and 4 labeled on your graph. Finally, you need to make sure your axes are labeled appropriately. That means like don't just have numbers there, but it should have units, like what units was it measuring in. Then you should also have a data table. For your data table, the first thing you would want to include was just the exact amounts and concentrations of the reactants that you used. This is very similar to what you did in the pre-lab questions, where you had to kind of predict exactly how many mils were you going to have of each thing and what molarity was it. This is just where we're looking for your exact amounts if they're any different. Then, of the data you collected, what we really care about is the slope. So you want to make sure that you have the slope for each part recorded in a nice table there so it's organized. I know that slope is usually printed on your graph, but let's get it in the table as well. Then we want to know what was the exact temperature you had. I know we were shooting for about 20 degrees on parts 1 and 2. Hopefully you recorded your exact temperature there. Obviously part 4 should be a little bit different, but we want that to be clear in your data table because that was again something that could change. Finally, do you have some qualitative observations? That could mean what did the solutions look like to start with? What did they look like after you mixed them together? What did you notice about what was happening in that test tube when they were reacting? When your data look good, you're ready to go on to the fun part, the analysis. The analysis of this lab is kind of like the questions and calculations all rolled into one. So for question 1, you're trying to fill in this table. The first thing we want to know is the initial rate for each reaction. Where are you going to get this from? Well, you want to know how fast a product was being produced, and that specifically was the oxygen you were measuring. So pretty much what we're looking for here is the slopes of those lines. Now, for many of you, when you look on your graph, it'll say that M value equals a number and then plus or minus some other small number. That plus or minus business at the end is like a statistics thing. It's giving an error bar. We don't need to worry about that, just what's the actual slope. Next, we want to fill in these columns that ask you for the concentration of both of the reactants after mixing. Now remember, those square brackets mean molarity. So we want to know the molarity of these chemicals. Now I know what you're thinking. You're thinking, I already calculated this in the pre-lab. I know that that hydrogen peroxide was something like 0.88 molarity. But what we want to talk about here is the fact that in this trial, you actually dumped 2 chemicals together. So you started out by having each one individually, and then you dumped them together. When you put those 2 solutions together, what you essentially did was a dilution, okay? Let me give you an example of what this is going to look like for your calculations. You should show these calculations so we know how you get these numbers that go into your table. If you think about part 1, you started with 4 milliliters of 3% hydrogen peroxide and 1 milliliter of 0.5 molar potassium iodide. So when you mix those two guys together, you had 4 mils plus 1 mil, which gave us a total of 5 milliliters of solution. Now, if you had slightly different numbers, if you had like 4.1 milliliters, then you would want to use that number, that exact number here. When we do a dilution, the equation that we have for this, if you will recall, is M1V1 equals M2V2. So what we know, for example, in part 1, is we know that the hydrogen peroxide, if I start with that substance, I know it started with an initial molarity of 0.88. If you don't know where I'm getting that number from, you need to go back and check your pre-lab questions. That should be like in pre-lab question 1, you should have the work to support that answer. At the beginning of that trial, I had 4 milliliters of it. When I finished the trial, I'm not sure what my new molarity was, but I do know that I had 5 milliliters total of solution. So from this, you should be able to solve for what M2 is here. That'll give you the exact molarity of the hydrogen peroxide after you dump the two chemicals together right as the reaction was starting. For the Ki, you can do the same type of thing. So you would use the exact concentration and volume that you had for the Ki to start with in that part, and then you know it went to 5 milliliters total. You'll need to do this calculation for each of the parts, although of course some of the numbers stayed constant. For example, I think you used the 4 mils of 3% peroxide in a couple trials. But you should show your calculations for that, and then those answers that you get can be filled in here. So I'll just put a note here that says from dilution. At this point, what you have is you have a data table. You'll see that it tells you for 4 different experiments what was the concentration of each of the reactants and what was the initial rate. Does this sound kind of familiar? If you think about the problems we've done for kinetics, you've been looking at tables like this to figure out rate laws and orders. Now we should mention that one of these parts should not be used in your comparisons. If you think about it, part 4 was done at a different temperature, right? Because it was a different temperature, that means that the rates are going to be different. So you want to not use part 4 when you're doing your comparisons. Stick with parts 1, 2, and 3. When you do those comparisons, you'll be answering question 2, where it asks you to find the order of the reaction with respect to both Ki and H2O2. So you've got 2 reactants you're trying to figure out the order with respect to, and notice, look at that, they want you to explain your logic. So make sure that you explain it well, tell what trials you're comparing, what stays the same, what changes, and what that tells you about the order. Now, because these are true experimental data, your numbers might not be perfect. For example, you might double one reactant and find that the rate neither doubles nor quadruples. Maybe it's somewhere in between. What I would do then is go ahead and use your calculator to divide out the ratio and find out exactly what it is, and then see which order that seems to be closer to. So is it closer to also doubling, or closer to quadrupling, or something completely different? So once you've determined those orders, you're now ready to write a rate law. Remember, a rate law has the form rate equals K times whatever your reactants are raised to their little power, right? So you would use your reactants here and your orders. I should clarify, it said right here determined in number 1. That was really what you determined in number 2. Oops. Once you have your rate law, hopefully you should be able to find the overall order. This should be like the easiest point on there, because all you have to do is add up the exponents. You're now ready to calculate the value for your rate constant K. Remember, to do that, what you have to do is plug in the numbers from the trial. We want to do this for each of the parts. So you're going to do the same calculation 3 times. Remember, the whole idea is this should be a constant. So for that reason, we're actually going to calculate an average value then. So you should hopefully find that parts 1, 2, and 3 have K values that are close to each other, and then find their average. Why should we exclude part 4? Well, think about what was different from part 4 and what that would do to the value for your rate constant. To figure out what exactly those units are, the units are especially weird on this one, like weirder than normal. The reason for that is if you look back at your data table, it's how we measured the rate. If you think about it, you were measuring a slope, and the slope you were measuring was for the production of a gas over time. So if you think about a slope as being a change in y over a change in x, look at your y-axis, what kind of units did that have? Some of you had it in kPa, some of you had it in ATM, or maybe you had a different pressure unit there. The denominator, the change in x you had, was a change in time. So that would be seconds down there. But what you'll find is that these units are not going to cancel out as nicely as our molarities normally do, so you will wind up with especially weird units on K once you do all the math of solving for your K. So going back then, make sure that you do include units on your answer, which we know will be really weird, but go ahead and go with them. At this point, you've done everything you needed, like calculation-wise. What we're looking at next has to do with the mechanism. They give you a proposed mechanism. They tell you which step is slow and which step is fast. And they want to know, does your experimentally determined rate law support that mechanism? In order to answer this, you're going to have to think about or look back in your notes, what do we know about how a rate law should go with a mechanism? And then yes or no, and justify your answer. You're now ready for everybody's favorite part of the lab report, the error analysis. When you do your error analysis, I'm going to have you come up with the errors here. We're looking for at least 3 sources of error. These should be experimental things. Don't tell me things like, maybe that we did our calculations wrong, or maybe when we measured out this chemical it wasn't exactly right. We want to know like what could have happened. You know, did something pop out? Did something not get mixed properly? Did something happen with the temperature? And from that, we want to know how would it have affected your data or your graphs. So was there a number specifically that it would have affected, made it get bigger or smaller, or just left it stay the same? Then you want to draw the conclusion about how that would have affected your results for the rate law and or the rate constant. So think about, would that have made it seem like something had a bigger effect or a smaller effect? Or what would it have done to your value for K when you calculated? At this point, then, you should remember to write a conclusion. Don't want to leave that one out. That's usually easy points in there. And then if you are choosing to do the extra credit today, you can use the Arrhenius equation, which is in your notes. And there's a form of it shown here. This form is slightly different from the form that was given in your notes. It's just rearranged a little bit differently. From this, we can figure out the value for the activation energy. In order to do this, so the EA is what you're trying to solve for. That means you have to plug in everything else. So it gives you a hint here about which value of R do you want to use, what kind of units do your temperatures need to be in, and these K's are indeed rate constants. Okay, so that's what you calculated a couple problems ago where you found the rate constants. To do this, I want you to think about which trials would you want to use to compare the effect that temperature has. So if we only want to look at the effect of temperature, think about which 2 trials you could use where temperature was the only thing different between them. Then you'd be comparing the values for K and T for those 2 particular trials. I think that's about everything. I hope this has been helpful for you guys. Good luck in writing those lab reports. I look forward to grading them.